Okay, what we're going to do today is talk about the analysis of a linear regression. What I have in front of me is the KC house data set that shows a bunch of transactions on a particular date of house purchase in Kings County. What I want is a dollar sign, right? And we're very interested in the price, and then as our Y variable, this is our independent variable. We're going to try to predict what the price of the houses are depending on certain other variables such as bedrooms, bathrooms, square foot and the size of the house. So we're going to use square foot living because we've used it before. Let me just kind of clean this up a little bit, kind of center up this top spot. So we're going to use these two. As a matter of fact, what I'm going to do is cut this guy and put it over here on the left. So I have square foot living and price together. These are the ones that I care about. Let's make them a different color so we can know if that's terrible. Let's make these a dark blue so that we can kind of see them a little bit differently. And what we're trying to predict in our variable is that the square foot living somehow predicts the price. I'm going to go ahead and highlight these, and before I start my analysis, I'm going to put together a classic scatter plot, just so that we know where we're headed. And that looks like there's some sort of linear regression here, and that's pretty good. Probably somewhere in here. It looks like maybe there's a different variable set over here. Maybe that's high luxury homes, but we don't really care about that. We're just focused on this line, and this is going to be our y equals mx plus b, or more to the point, price is equal to b sub 1 square foot plus our b sub 0, or our intercept. And that's what we're going to do. And this video is not just about regressing that, but to try to analyze what that looks like. So let's go back to the top of our data set. And let's go ahead and run a regression. I'm going to hit data analysis, and under data analysis, go down to regression, hit OK. And I want my Y range to be price, right? So I'm basically going to hit price, Control Shift down. I like that. I'm going to go over to the X range. I'm going to erase that one, and I want that to be C. You can see, if you're looking at the numbers, that we're looking for about 500 observations here. That's just the data set as I cut it. In this case, we are going to use labels because, we are going to use labels because I've grabbed the top of the thing. I'm not going to change the constant. Everybody else stays the same. I'm going to hit OK. And we get a very traditional regression output. I'm going to delete this upper and lower stuff. We don't need it. It's just going to kind of get in the way. And we are looking at traditional regression results. All right, so let's zoom in a little bit and walk through these so we can talk about what they are and why we care. Multiple are the ones that I care about include R squared. All right, so I care about R squared. I care about observations. And the other ones are also important, but I'm not going to worry about them right now. These are kind of like the big ones, the ones I'd like you to focus on, and what they mean. R squared answers the question, how much of the data, or the variance, how much of the variance really, but how much of the data, the observations, does this model explain? And we calculate R squared based off of our squares in the ANOVA table, but let's not worry about that too much right now. I would focus right here on the first 3 or 4 decimal places, and because R squared has to be between 0 and 1, it kind of sort of says, hey, look, we can explain 0.468, or we can explain 46.8% of the data, of the observations. What we're saying is about half the data can be explained with this model, which also means that about half the data cannot be explained by this model. It's very traditional in many research industries, research, journals, academics, or whatever, to seek an R-squared value that is greater than 0.90. There are many other places, such as the finance and the economics guys, who turn around and say, "Hey, look, the macroeconomics will get you up to 0.9. We don't care about that. So if you have an R-squared value that's less than 0.9, that's perfectly acceptable." Undergraduate projects, from in my case, if you're less than 0.9, that's fine. But you should have a sentence that says in your research project, R-squared value equals 0.468. Therefore, we can explain away 46.8% of the results. Observations are self-explanatory. We have a total of 500 observations, which we then use to calculate stuff like degrees of freedom. But what you're really saying here is that you have, if you go back to your stats 1 stuff, you want to know that your observations are greater than 30, right? The more, the better. But if you have too many, if you have 500,000, then everything appears significant, and then you have a different debate. But you really just want to report this in your paper so that other people know what the data set kind of looks like, right? And then we can move on to our ANOVA table. Our ANOVA table is great for ANOVA people, but we really care about the F-stat, and we really care about the significance, right, of the F-stat. And now this is really interesting because we have this e to the negative 70. And if you do this if you run this particular regression in Excel, as opposed to some of the other fancy statistical softwares, you're going to get results. If you have a good regression, you're going to get results that kind of look like this. And what we're saying is this is 0.0000000 all the way to 71 decimals, 2416, right? And so that's just kind of ridiculous. We're not going to do 70 zeros in this case. So let's erase all of this. And we're basically saying that our significance here is 0.000002, right? So for all practical purposes, you will often see 3 decimals when we talk about significance, and you'll see 000. And so this is a perfectly acceptable report for the probability of F, and that makes sense, right? Let's draw our F. Let's draw our F statistic real quick. My F statistic, or our F distribution anyway. The F distribution looks something like this, and then we go on. The F-stat 438 is way off the screen over here somewhere. So the area right of the curve is so small that it is 0.00000000000 and so on, right? If this is 438, then it's going to be, it's probably not even on the screen. It's so small. Let me redo this so that you guys can see it. If it's way out here, 438, then the area under the curve is so small that the area is 0.0000000 and so on. I mean, just crazy small. It is so small that if we were to set our alpha at 0.01, somewhere in here, and we knew that the area under the curve this way was 0.01, we would be rejecting, and this is 0.01, we would be rejecting our null hypothesis, and we would therefore say that we have a good regression. So if alpha is equal to 0.01 or 0.01, it's terrible, 0.01, would we reject the null hypothesis? Well, the question is this one smaller? Is our statistic smaller than our alpha? And the answer in this case is yes. So we reject the null. Therefore, we have a good equation, right? This guy tells us, answers the question, is this a good model or a good regression? Is this a good model? And the answer is yes, right? How do you know? Because it's less than alpha. The other thing you can do here, and I'm going to run out of space here in a second, is you can turn around and say, I can also test alpha at 0.05, and I can also test alpha at 0.10. right? By taking one good look at this, I can test all of them. And the answer is reject the null, reject the null, reject the null. This regression model is acceptable at 0.01, 0.05, and 0.10 because I answer the question, is it smaller than alpha? And the answer is yes, it is, yes, it is, yes, it is. You can report all three and still answer the question, is this a good model overall, right? So that's nice and that's good. And now we're going to move past the ANOVA table and talk about our actual coefficients. I don't care about intercept. I do care about the coefficient, right? So this answers the question. The next thing I'm going to ask is this positive or negative? Because this answers the question, what is the relationship between my dependent, which is my x, and independent, which is my y, variables? Is it a positive relationship or is it a negative relationship? In the case of the one we just had a minute ago, we had all of these dots and they look like this, and there's an upslope, and so this is a positive sloping line. We have a positive relationship, right? That's good. It answers that question. So that's good. It's positive. Sometimes you'll get a good result. You'll get a nice positive coefficient. And then you'll look up and say, oh, I got what I wanted, but I didn't get the significance. Or I had a really, really low R squared. Well, that's great. You're going to have to go back to the drawing board and figure out how come you got what you wanted, but you didn't get the other stuff. You got to go back and look at the data again, right? Finally, we tested the actual model. We tested our regression line. We want to test the coefficient. And we do that by calculating our t-statistic. We do that with standard error. We'll do that separately. More to the point, we go back to this p-value. The t-statistic will then obviously calculate your p-value. And what we're going to do here, you'll notice that we're still at e negative 70. So this is, in effect, 0.00000000000, just like the other one before. We're going to leave it at 3 decimals because that's just, what we do academically. And therefore, it's what we do in the business world when we do comparative stuff. And I'm going to do the exact same thing before. At alpha equals 0.01, I'm going to ask the question, is this bigger than alpha? Sorry, is this smaller? Is this smaller than alpha? And the answer is yes, it is. Therefore, I reject the null hypothesis that this is a bad, reject the null hypothesis that this is a bad coefficient. Therefore, this is a good coefficient. I'll use stats 2 people should know what I'm talking about here. I can also automatically do it for 0.05. I can also automatically do it for 0.10. And the answer is no matter what alpha I pick, 0.000 is good. This value here answers the question, do I have a good coefficient? Okay, so let's talk about the big 4 questions that you should be asking when you talk about regressions. Okay, number 1, R squared. How much of the data does this model explain? Okay, 46%. Okay, got it. Number 2, is this a good model? Well, is this p-value smaller than alpha? 0.01, 0.05, 0.5, yes, yes, yes. All right, so we have a good model. Okay, excellent. The next thing I'm going to do is say, what is the relationship between my dependent and independent variable? What is the relationship between my x and my y? In this case, the answer is I have a positive relationship. What does that mean? As x increases, y also increases. Got it. Okay, finally, is that a good variable? Okay, do I have a good coefficient? You could scratch this out. You could put variable here. Do I have a good variable? And the answer is my p-value is smaller than 0.01, 0.05, 0.10. Therefore, I have a good variable. This is a nice regression. It is a simple one variable linear regression. It explains half the data. Absolutely. Does it make sense? And finally, the last thing I would ask myself, does this make sense, right? I wouldn't put this question into a research paper, but does it make sense? Does square footage explain price? Well, yeah, that makes sense, right? The bigger the house, the bigger the square footage of living space inside a house, the more expensive that house is going to be. For the most part, that makes sense. Are there other variables that explain stuff like location and 2 stories and waterfront view and all the other stuff? Yeah, obviously. But if we just look at this one variable, does this make sense? Yeah, it makes sense.